Our last example before you continue to work is a problem that asks about the interval of convergence and the radius of convergence for a given series in sigma notation. So what looks different about this one as compared to the others that we've done? As an exponent, exactly. And if we are finding an interval of convergence, the interval we're talking about is with respect to x. So from an x value to an x value, the series models the function. Okay, so that's what we're finding is where that happens. All right, and anytime it asks for interval of convergence or radius of convergence, we are using ratio tests. How do I set up ratio tests? Yep, we're going to have L equals the limit as n goes to infinity of the absolute value of x to the n plus 1 over
n plus 1 through n plus 1.
Good. N plus 1 root n plus 1
Times 3 to the
times 3 to the n plus 1. So we have the n plus first term over the nth term, x to the n over m root n, 3 to the n. All right, and just like we did yesterday, we want to be neat and organized and line up the corresponding parts. So this becomes the limit as n approaches infinity, the absolute value of what over what? Good, x to the n plus 1 over x to the n times let's do n root n over n plus 1 root n plus 1 times 3 to the n over 3 to the n plus 1. Have we accounted for everything? X's, 3's, and n. We're good. Now let's simplify a little bit. X to the n plus 1 over x to the n. Limit as n goes to infinity of the absolute value of x. Now let's go ahead and take this limit because it's actually set up pretty nicely. What's the power on the top? 1.5 or 3/2. What's the power on the bottom? Remember, the plus 1s don't matter when n approaches infinity. So it's also 1.5, correct? Or 3/2. So we have n to the 3/2 over n to the 3/2. Giving us same power on top and bottom of what L'Hopital, that would give us 1. That's lovely. And then times what? 1/3. So actually I have taken the limit already. We don't need that there anymore. L equals that. Now, what has to be true for this to converge? Our limit has to be less than 1. So we want to take our simplified expression, which will still have an exponent, may still have an exponent, and set that less than 1. So we have x over 3, absolute value is less than 1. We set up our compound inequality, and that becomes what? -1, less than x over 3 is less than 1, and we solve that by multiplying by 3. That is our open interval of convergence. Now, what we want to know, so we know the general open area where the series overlaps the function or the series has a finite sum. We need to know if that includes -3 and 3 or if it does not include them. That's what we call testing the endpoint. Which means to plug in x equals -3 and let's try that again. There we go. X equals 3 and x equals -3 into the original series. So, 3 to the n plus 1 times 3 to the n plus 1 to see if it converges or diverges. And to test for convergence. Alright, so our original series was the sum from n equals 1 to infinity of x to the n over n root n, 3 to the n. So instead of writing x, I will write x equals negative 3. We've got the sum from n equals 1 to infinity of, in parentheses, negative 3 to the n over n root n, 3 to the n. Is everyone okay with what I did there? You need to remember what we find in our interval, they are x's. So we're not plugging that in for n, we're plugging it in for s. Alright, well now to figure out what's happening, write out the first few terms. Always helps to write out the first few terms. So when I have n to the first, I get negative 3 to the first over 3 to the first. What is that? Negative 1 over, I put 1s in for the n. Negative 1 over 1. Yes? Okay. When I plug in 2, I get negative 3 squared, which is positive 9, over 3 squared, which is 9. So that is 1, positive. And then I put in 2s here and here. 2 root 2. So what do you think the third one is? And good. Minus 1 over 3 root 3. So now we need to determine if that converges or diverges. What jumps out at you? Alternating. It is an alternating series, so let's use the alternating series test. First off, strictly alternating? Check. Second, the limit as n goes to infinity of the absolute value of our a sub n, what would that be? Well, let's think about what it is. The absolute value of this basically makes this 3 to the n over 3 to the n, correct? And that's just 1. So this simplifies to 1 over what? N root n? N root n. And does that limit go to 0? Indeed it does. Finally, you want to look at the n plus 1 term versus the nth term. Yeah, Lauren?
Where did you get 1 over n root n?
Well, when I take the absolute value of this, of a sub n, I end up getting rid of that negative. The absolute value takes care of the negative. So let me show you. And then they cancel. Okay? But that's for the 1 over n root n comes from. So now we need to look at the n plus 1 term versus the nth term. Again, this negative 3 to the n over 3 to the n is just going to make a negative 1 or a 1. So really what we need to look at is 1 over n plus 1 root n plus 1. Is that always going to be less than 1 over n root n? N plus 1 is always bigger than n. Root n plus 1 is always bigger than root n. So this denominator will always be bigger than this denominator, which means that this fraction will always be less than that fraction. Check. Okay? So this is convergent by the alternating series. So what this means is in my open interval, I'm going to have x, where I had x is greater than negative 3, I'm going to see greater than or equal to. All that work is a little equal sign on our inequality. So that's for negative 3. Now what? Now we have to do the same for 3. X equals 3. So we get the sum from n equals 1 to infinity, 3 to the n over n root n, 3 to the n. This one comes out even nicer. What happened? You don't need to. Do a little work on it first.
Oh, yeah, you can say the way.
Yep. This is 1 over n root n. Okay, but we're testing to see if this series converges. We're not taking just a limit. What type of series is that? You should be able to look at it now and say, what is it? No? It's a p-series. This is a p-series. 1 over n to the what? 3 halves. It is a p-series with p equal to 3 halves, which is greater than 1, so it converges. So remember I said for the p-series and the harmonic, in the process, if we come across it, you should be able to look quickly and tell and not have to go through some exhaustive test. So that's what you want to hope happens when you're testing it. It comes out that way. So our answer is our interval of convergence is x is less than or equal to 3 and greater than or equal to negative 3. What about our radius of convergence? Half of that distance. And what would that equal? None. Okay? Any questions? Yes, Jack.
So if we don't use the P3,
Negative 3 came out being alternating here, so this is not. Negative 3, when we wrote it out, became negative 1 over 1 plus 1 over 2 root 2. Because you can't cancel these unless you get an absolute value of it. Yeah, so we can't just call it a p-series. All right, anything else? Questions on that?
So you go back down.
Yep.
In your radius, just
Is that little, is it recording? Can you see the thing moving?
Yeah.
Okay, good.
which we don't hear.